In this video, I'll cover the question on contingency tables, a few more calculations, and the calculation of odds. In this calculation, this is a contingency table, and we have some sick people, although they don't have to be sick people. They might be sick capacitors on the test. But we have sick here, healthy here in these columns. So the total number of sick people is 240. The total number of healthy people in the study was 11,760, giving a total of 12,000 people. They had a test. 36 of them came back positive. 10,664 came back negative, and then we just divide it according to the table. Remember, TP means true positive. A sick person getting a positive test, that's a true positive. They have the disease and the test says they have it. The true negative is a negative test result for a healthy person, a person without that particular disease. The others are false. It's a false positive if a healthy person tests positive for a disease they don't have. It's a false negative if the sick person tests negative for a disease they do have. In the written lecture and also on the homework, I discussed some special names for some of these calculations. For example, there was positive predictive value and negative predictive value, sensitivity, and specificity. Okay, you do not have to know those names. I just want to introduce that vocabulary so later on in medicine or in some other field, when you encounter them, you'll have heard those words before. Instead, the test tells you exactly what has to happen. Compute the probability that a sick person got a positive test result. Well, there were 160 positive test results out of 240 people, and there's your answer right there. You could reduce this one a little bit, right? But ordinarily, you do need to write this fraction. What's the probability that healthy person scored negative? These are for the true negatives. Well, there were 10,584 negative tests for healthy people. Total number of healthy people, 11,760, and that's your answer in that case. So the calculations that you'll have to do for the contingency table will be spelled out. You do not have to know the word sensitivity, positive predictive value, or any of those others. For this question, there are 8 eligible people for a game show. 3 people can be on the show. And the idea is to find the number of possible groups of contestants, assuming that order of being chosen doesn't matter. Since order doesn't matter, this is combination. Remember, the combination for n objects taken r at a time is n factorial over n minus r factorial. That's the same as the permutations, divided also by r factorial. You can see that's substituted here. The n is 8. So you see the 8 right here, 8 factorial. Then 8 minus 3 factorial is right here. That's the same as this term. And then it's divided by 3 factorial, which is the r factorial. Now you should work this out a little bit. It's not bad. So by working out the parentheses, I have 8 factorial over 3 factorial times 5 factorial. Whoops, didn't get the pen. So I'm sitting here with 8 factorial over 3 factorial times 5 factorial. So count down the 8 until you can cancel something in the numerator, in the denominator. Of course, you want to cancel the largest thing since that's most troublesome. Now there's no more factorials to cancel, so you have to work it all out. 8 times 7 times 6 divided by, there's a 3 remaining. Remember, when you cancel things, they turn into ones. 3 times 2 times 1, 3 times 2 is 6, so this whole thing goes away, and that answer is just 56. So there's 56 different combinations of 8 people taken 3 at a time for the game show. That's the combinations. Now this is a probability problem again, and the probability that the letter chosen at random will be either a B or a D. So here's your OR. And in the reference section, I've rewritten it with B and D instead of A and B. Here's the formula for calculating the probability of B, event B, or event D. You add the two probabilities and you subtract any overlap. Well, what about B and D? If you're going to choose a letter at random, if you choose B, you can't choose D. If you choose D, you can't choose B. In other words, B and D are mutually exclusive, so that final term here is 0. So this is just the probability of D plus the probability of B. Well, to pick D out of the alphabet is 1 in 26, since there's only one D. Same for B. It's 1 out of 26. And you can add that 2 out of 26, get 1 out of 13, and leave it like that. In this problem, you need to compute the probability of not rolling a 3 on a regular 6-sided die. Well, if you don't roll a 3, that means you roll either a 1, 2, 4, 5, or 6. Well, the long way is to compute the probability of rolling any of those. But an easier way when you have a not in there is to compute the probability of rolling the 3 and then use the idea of complement. Right, the probability of rolling a 3 is 1/6, 1 out of 6, because there's only one 3 on and 6 sides. Now the probability of an event plus the probability of its complement equals 1. So I can turn that around. If I want the probability of the complement of rolling a 3, which means not rolling a 3, then I can turn this around and get the probability of A bar, which is the complement of A, equals 1 minus the probability of A. Well, that happens to be 1/6, so I subtract 1/6 and I get 5/6. The next little problem down here, which you can't read very well. Let me try to. Okay. Give the maximum and minimum values of probability for any event. We should be able to get this pretty easy. It's either going to be 1, it'll be 1 for the maximum and 0 for the minimum. When the probability is 0, it means the event will never occur. If the probability is 1, it means it will always occur. For example, if you're rolling dice, the probability that some number will show up is 1. There will be some number. The probability of a specific number will have a probability between 1 and 0. And here's the final question. This is a lot longer test, I know, than the first test, but on the first test I made you do, for those first 3 chapters, you had to do a lot more work. You had to read that extra article, and it was just the start. So that's why this test is longer. Okay, and here's the last question on it. And it's just about the same as that probability for not rolling the 3, but it's a little different. What is the probability of the complement of A if the probability of A is 1/3? Well, it's as before. You can you can remember this equation, that the probability that A will occur and the probability that everything except A will occur is all the space, is everything, all possibilities, and it's a probability of 1. So by subtracting the probability of A and putting it on the other side, we get this equation. Since A is 1/3, we subtract it and get 2/3. What are odds? The odds that an event will occur. The odds is the probability of A divided by the probability of its complement. That's odds in favor of event A occurring. Right. The probability of A was 1/3. The probability of the complement of A was 2/3. This becomes 1/2. If you're still struggling with these complex fractions, 1/3 divided by 2/3, remember that this is the long way to do it, but it explains all the steps. A fraction is a division problem in disguise. You divide the numerator by the denominator. How do you divide fractions? You turn that into a multiplication sign and you flip them over. Now you can cancel the 3's and you get 1/2. The fast way to do it is to say these denominators are the same and they can be canceled. You end up with a 1/2 also. So 1/2 is written as 1 to 2. So the odds in favor are 1 to 2. What are the odds against? The odds against the event occurring, so the are the probability of the complement divided by the probability of A. In this case, it'd be 2 to 1 that the event won't occur. And that's the end of the test for Chapter 4 for statistics.